All righty, friends, welcome back. So we're looking at Unit 8, final exam review related to stoichiometry. Quick suggestion, if stoichiometry is not really a topic area of emphasis that you have had a lot of success with, I tend not to try to spend too much time on that section in the final exam so you can maximize your time. Anyway, let's get right at the heart of reviewing this. So stoichiometry is about the relationships between what we call reactants, right? The particles on the left side of a chemical equation, and what they turn into, called the products, or the ratio of one reactant to another reactant. It's about chemical quantity ratios that are described by balanced chemical equations. So if we read item 1, it's asking us to identify the mole ratio of hydrogen gas to oxygen gas from the balanced equation. So the mole ratio is simply the coefficients. So it says hydrogen gas. Well, that can't be H2O. We know that's water. So that's this, right? The coefficient for hydrogen gas is 2. Oxygen gas, again, that can't be H2O. That's water. So there's no coefficient in front of that O. So that means it's 1. So our ratio would be 2 to 1 for that particular example. If we look at number 2, it's asking for the mole ratio of methane gas, CH4. Well, there it is, 2, to carbon monoxide gas. Carbon monoxide is CO. Remember, H2O would be water, O2 would be oxygen. So it looks like the ratio is 2 to 2. So you could either say 2 to 2 or a simpler reduced version of that, 1 to 1. So identifying mole ratio is relevant to being able to deal with what we call stoichiometry relationships. Okay, so the simplest version of a stoichiometry problem would probably be described as a mole-mole problem, where it says take mole of one chemical and relate it to the equivalent mole of another chemical that is somehow related to this particular chemical reaction. So when we read the words, there's a given amount. Look for the given, look for the chemical as well. 3.76 moles of oxygen, you place the given amount. Look for the desired amount. How many moles of water vapor? So what you're going to do on the bottom of the fraction is you're going to put the desired amount, X moles of water vapor. On the right side, make your labels match. Mole of O2 over mole of H2O, and then just pull the coefficients from the equation, right? H2O, there's a 2, right? So we put a 2 on the bottom. O2, there's a 3, so we put a 3 on the top. And then we cross multiply to turn it into an equation, X times 3, 2 times 3.76, right? We get 3X equals 7.52. Divide each side by 3, it would require 2.51 moles, so they're related by mole ratio. On the right side over here, for those folks who may be using dimensional analysis, I demonstrated the math. If we start with the given, we cancel the given, turn it into the desired, and we used the mole ratio to do that. Okay. Number 4 is a similar question. There's a given amount and a desired amount. It's a mole-mole problem. So it says start with 0.72 moles of calcium sulfate. That can't be this, Ca, because that doesn't have any sulfate with it. So here's our calcium sulfate, and it says how many moles of aluminum sulfate. So aluminum sulfate is this guy, right? So we're relating the pink to the blue here. So we start with the given, right? We start with the given. And we place that over the desired X, the unknown amount of aluminum sulfate in moles. On the right side, we make the labels match. Mole of CaSO4 over mole of Al2SO4, and 3 to 1, right from the coefficients in the balanced equation. You would then cross multiply, turn it into a formula, not a formula, I keep wanting to say formula, an equation. 3 times X is 3X. 0.72 times 1, 0.72, divide each side by 3, and 0.24 moles would be the required amount needed to form 0.72 moles of calcium sulfate. Okay, so that skill, that organizational skill is needed to do more complex versions of stoichiometry. So in number 5, it's asking us to identify limiting reagent. So let's just quickly review that. Basically, these words say that there are 2 piles of chemical reactants, 7.5 mole of nitric acid. I'm putting a little 7.5 there. 15.7 mole of magnesium. One of these piles is going to get used up, and there'll be extra left over of the other. So to understand which one is the limiting reagent, either the magnesium or the nitric acid, a really good strategy for doing this is pick any product on the right side and determine what product you'd like to try to turn it into. So I chose H2, and I said, well, let's just make the mole amount of H2. So I started with 15.7 mole of magnesium, and I did exactly like I did above. I made magnesium become hydrogen gas by using the given amount, 15.7 mole of magnesium, over the desired amount, X mole of hydrogen. And then on the right side, I used the mole ratio, 1:1, right? 1 mole of magnesium, there's no coefficient. 1 mole of H2, also no coefficient. I cross multiplied, right? When we cross multiply, we see we get 1x, or x is equal to 15.7. So basically that means 15.7 moles of magnesium will create 15.7 moles of hydrogen. So now we're going to do the same thing with the nitric acid. We're going to see how many moles of hydrogen nitric acid could make. So we organize that given over desired. We start with the nitric acid, but now the nitric acid has a coefficient of 2. So 2 mole of HNO3 goes on top on the right, right? H2 still has a coefficient of 1, right? We cross multiply, 2x equals 7.5, divide each side by 2. And that means that if we started with nitric acid would only make 3.75 moles of H2. So nitric acid, HNO3, makes less product, and we say nitric acid is the limiting reagent as a result. So the limiting reagent has to be a reactant. It's the reactant that runs out first. Mathematically, it'll be the one that creates the least amount of product that you decided to calculate. So on the right side here, you're going to see the same mathematics demonstrated with that other strategy called the dimensional analysis, where we cancel out the given to turn it into the desired, and we get the same quantities as we did on the left. So what we see in number 6 is really the same thing as we had in number 5, just another practice example. If you wish to, sometimes it's easier to understand if you do a little bit of labeling. So 72.9 moles of potassium chlorate. That's how much you have of this reactant. And phosphorus, P4, you have 21.8 moles of that. So one of these piles is going to run out. We would call that one the limiting reagent. And the way we determine which one runs out is we pick one of the products on the right and we make a product amount from each reactant. So here we started with P4, phosphorus, and we said, okay, let's make it the amount of P4O10 that this could make in moles. So we set up the given over the desired, X mole of P4O10. We plugged in the coefficients, 3 mole of P4, 3 mole of P4O10, that comes from the balanced equation. We cross multiplied, right? 3 times X is 3X, 21.8 times 3 is 65.4. We divided each side by 3, and this would make 21.8 moles of P4O10. We did the same thing with the KClO3. We chose the correct coefficients. We made the amount of P4O10 that it could make, and we noticed that it can make 21.87 moles. So the 72.9 moles of potassium chlorate makes a little bit more product than the phosphorus, the P4. So we say the phosphorus, P4 is limiting. It makes less product. So the next few examples are just standard Stoic problems. There's a given amount and a desired amount, and we organize these the same way each time. So it says we have 87.2 grams of aluminum as the given amount. We want to see what mass of iron that could make. So we put the given grams of aluminum over the desired X grams of iron. What we then do is we put the quantities on the right in grams. We make the labels match: grams of aluminum, grams of iron, right? Grams of aluminum, grams of iron. We make the labels match. We put in the quantities equal to 1 mole. That comes from the molar mass of these elements. Periodic table says 26.98 for aluminum, 55.85 for iron. Because these are elements, there's nothing to add up. We go back to the balanced equation. We see 2 mole of aluminum. So we got to factor that in. 2 times 26.98. We see 3 mole right here, 3 mole of iron. So we got to factor that in, right? 3 times 55.85. We cross multiply. 2 times X times 26.98. 87.2 times 3 times 55.85. Hey, look at that. We get an equation. We divide each side by 53.96. And that would relate to 271 grams of iron. So it's given over desired. Make the fractions match on the right side. Make certain you factor in the mole ratio quantities, the multipliers. So I demonstrated that same calculation using the dimensional analysis strategy. The given grams of aluminum, we turned it into moles of aluminum. We turned the mole of aluminum into mole of iron. And then we turn the mole of iron back into grams of iron, and you end up with the same answer using that strategy. Number 8, same setup, right? There's a given amount. It says what volume of oxygen as a result. So we put given liters of carbon dioxide, because that's what it says, over liters of oxygen, volume. On the right side, we put the quantities equal to 1 mole, but we make the labels match: carbon dioxide over oxygen. There's always 22.4 liters equal to 1 mole, as long as it's at standard temperature and pressure. We factor in the multipliers, right? For carbon dioxide, there's a 4 coefficient. For oxygen, there's a 7. So they get multiplied. We cross multiply, turns it into an equation. 4 times X times 22.4 is 89.6. 83.8 times 7 times 22.4 is this 13,193. Divide each side by 89.6. We get 147. Same idea generated with dimensional analysis over here, right? You start with your given, you turn it into a desired, you continue canceling till you get the amount you want. Okay. So we got a question here about theoretical yield. What you're going to notice, I highlighted here, there's 226 grams of aluminum sulfide and 177 grams of water. Well, what's going to happen is one of these piles is going to run out. So what we decided to do is to find out, well, let's find out which one runs out first, because that's going to be the limiting reagent. And the way we determine the limiting reagent is we turn it into either product. So we either can make it the H2S amount, or we can make it the aluminum hydroxide, ALOH3 amount. So if you notice here, it said later, we want to know what mass of hydrogen sulfide could be produced. So I chose to make these reactants turn into the amount of H2S that they could each make. So there's 2 separate example problems down here. We started with 226 grams of aluminum sulfide, and we said, hey, how many grams of hydrogen sulfide could that make, right? Our given over our unknown desired, right? Our blue compared to our pink. Then we put the quantities equal to 1 mole in grams for aluminum sulfide. 2 aluminum, 3 sulfur adds up to 150.17. For hydrogen sulfide or H2S, that adds up to 34.09. We factor in the multipliers called the coefficients. There's no coefficient in front of Al2S3. There's a coefficient of 3 in front of H2S. We cross multiply. When we do that, we get an equation, right? We solve for X. So aluminum sulfide would make 153.9 grams of hydrogen sulfide. Then what we got to do is we got to see, hey, how much hydrogen sulfide could this mass of water make that we were given? So we did the whole thing all over again, but we used water as the given amount. So what essentially we did was we went away from using this as the blue info to this. Our given is now our water amount, 177 grams. Our desired is still hydrogen sulfide. We want to see how much hydrogen sulfide could be made. And on the right side, we put the quantities equal to 1 mole. For water in grams, it's 18.02, right? We add up the mass, 2 H's and 1 O. Again, for hydrogen sulfide, it's 34.09. We factor in the coefficients from the balanced equation. For water, it's 6. For H2S, it's still 3. We cross multiply. 6 times X times 18.02, we get 108.12. 177 times 3 times 34.09, we get 18,101.79. Divide each side by 101.82, 167 grams. So the Al2S3, or aluminum sulfide, could make 153.9 grams of hydrogen sulfide, this value, and the water could make 167 grams of hydrogen sulfide. So aluminum sulfide, Al2S3, should say 3 there, is limiting. It produces less hydrogen sulfide. The mass of hydrogen sulfide that could be made, well, that's related to what you run out of. Since we run out of aluminum sulfide first, the mass that we calculated right here, that's the most hydrogen sulfide you'd possibly be able to make based on stoichiometry. So the last part, part B, says how much excess reactant remains. So that's really just another Stoic problem. You start with what you know to be the limiting. We already determined limiting is Al2S3, and you turn that into the amount of the other reactant, water. So aluminum sulfide is going to run out. We know that, right? What we do is we put on the bottom the water amount, right, as unknown. What that calculation will do is that will calculate the amount of water that is actually required. What the words gave us is what amount we had in our pile. 177 grams of water is available, not necessarily required. So we do this Stoic problem, right? We organize given over desired, right? The desired is grams of water. We factor in on the right side the mole quantities, right? Quantities equal to 1 mole are 150.17 grams of aluminum sulfide, 18.02 grams for water. Put the coefficients in as multipliers, cross multiply, solve. You're going to get an amount of water, right? That amount of water is the required amount. To use up all of our aluminum sulfide requires 163 grams of water. Well, in the pile, we have 177 available. We compare the available to what we calculated called the required, and we would have 14 grams of water left. So there we have how we kind of calculate an excess reagent from everything works through the limiting quantity. When we know the limiting amount, we can calculate the quantity of any product produced. When we know the limiting amount, we can calculate how much extra reactant or excess reagent we have left over. And that's what we just demonstrated for part B here. Okay, percent yield is actually a chemical formula that relates to stoichiometry. Stoichiometry provides a theoretical amount. In a laboratory setting, we get what we call an actual amount, and that often comes from the words of the problem. So when we go and read this, right, look at what the words of the problem say. 29.9 grams of phosphorus tribromide was formed in the lab. That is actually an actual amount. So we're not going to do any calculations with that yet. We're going to hold that aside for now. What we are going to do is we're going to start with bromine, right? This guy right here, Br2, and we're going to see how much PBr3 or phosphorus tribromide, bromine could produce. We call that the theoretical amount. So we set up a Stoic problem, given over desired, bromine over PBr3. We put the quantities equal to 1 mole on the right. We factor in the mole quantity or mole ratios. We cross multiply 3 times X times 159.8, 37.3 times 2 times 270. We get an equation by doing that. We divide each side by 479 and look at what we get. The theoretical yield. This is how much PBr3, right, we could make. We could manufacture 42.1 grams from 37.3 grams of bromine. The word said what we got in the lab was only 29. So percent yield is a percentage. What we actually got was 29, right? What we were supposed to get was 42. So here's what we do. Actual over theoretical times 100. And that would give us 71% yield. So stoichiometry can be a little bit of a bear, especially when we're under time restraints. So once again, if stoichiometry is not really one of your fortes or strengths in chemistry, my suggestion is on the exam, don't spend a bunch of your time on the stoichiometry. There's not going to be a ton of stoichiometry to review for that exam because you just don't have time to do a whole bunch of that. So I hope you found these tips or strategies useful. Until the next time, this is Mr. Brewer.